Hey everyone, it is Mr. Canfield. Today in BC, we are going to be looking at arc length and area of a surface of revolution dash classwork. There, I can read. Cool. So, let's explain what that means. Arc length. We'll talk about this one first because it's written first. This is where like you have some curve, right? So we have in the past, we've found the area under this curve. We've also found the slope of this curve at some point. So we've done integrals and we've done area, or derivatives. Now we are going to apply the concept and yeah, we're going to find the length of some arc. And the way that we find the length of an arc is similar to when we found area. We generalized this idea where we took a whole bunch of rectangles and we added these rectangles. We found this easy area of a rectangle and we added an infinite number of those together, and that wound up being the integral from, a to b of f of x dx. This was the exact, this was the approximation. The exact was where we made an infinite number of these, squished them infinitely close together, and added them up. So we're essentially going to do the same idea when we're doing arc length. I'm going to go through the concept now, but the you really just need to know the formula. If you know the formula, then that's all you need. But the idea behind arc length was, so for area, we found like one rectangle. Well, here, why don't I find like one line segment? Like, how could I find the distance between 2 points? And if you don't have the distance formula memorized, you don't need it. If we think about this as being like x1, comma y1, this is x2, comma y2, well then, if I just like pretend this is super zoomed in and this is like a perfectly straight part here. Well, sorry, no, I'm getting ahead of myself. If I find this is close to the real thing. And then what we can do is we can eventually shrink this down and make it really, really tiny. But if I want to find that hypotenuse there, well, can't I just find out? So like, I could say that this here is going to be like a squared plus b squared, and then take the square root of it, right? So like, well, a squared is going to be this distance here, which is going to be x2 minus x1. And then this distance here is going to be y minus y, y2 minus y1. And then take the square root of that, and that'll be c, our hypotenuse. And then we'll just integrate this. Sorry, so I'm getting ahead of myself. Right, so that's going to be, that would be this piece right here. And then if I wanted to find, an infinite number of these little tiny things, all I need to do is integrate this from a to b. The problem is I have different x's, I have different y's. I don't have a single variable in here, so I need to figure out a way to generalize all of this and turn it into a single variable. So let's see. Instead of calling this x1, y1, let's call x1, y1 x, comma, f of x. And instead of calling this x2, y2, let's call this, shoot, does he, like x plus h, comma, f of x plus h. And you might be like, wait, we're starting to go somewhere with this. This reminds me of something that I used to see before. Well, let's see what happens if we go in here. So x2 minus x1. So that's going to be x plus h minus x, and then square that, plus f of x plus h minus f of x, and square that. And that's going to be equal to our hypotenuse at just one of our hypotenuses. Wait, x plus h minus x, we get some canceling that happens there. We have h squared here now. This is really close to being something nice. If you remember the definition of the definition of the derivative says f of x plus h minus f of x all over h. So if only this had said over h like that, then we would be able to, like, that'd be nice, but it doesn't. So what we're gonna do is we're gonna use a little trick here. And again, I am deriving a formula right now. You don't need to understand how to derive all this. We're gonna end up with a formula that we can use, and it's gonna be a really nice formula, don't worry. So what we're actually gonna do here is we're gonna multiply the top and the bottom by h. But there's a squared here. I put it on the wrong side of the parentheses. We're gonna multiply the top and the bottom by h. So if I do that, I still have this squared outside. I have an h times it. But now I have f prime of x. Because, just a reminder, and I'm taking a little bit of liberty here by, I'm ignoring the, I guess we could throw the limit out front of this kind of thing. We're taking the limit as h goes to 0 sort of thing. But the key thing is this now says h times f prime of x. And if you remember what h is, h was the same thing as delta x, which is the same thing as dx. And so this is really saying the square root of dx squared plus d, wait, shoot. No, okay. No, I know what I'm doing. So this is gonna be dx squared times dy dx squared, right? And that's gonna be equal to c. So this is where this gets a little bit silly. And if you're like, what do you mean this is where it gets silly? It's all right. So what we do after that is we say, well, you know what? I could factor a dx squared out of both of these terms, right? There's a term here, there's a term here. So if I do that, then I'll have a 1 left over here. That'll cancel, and I'll have a dy dx squared here. And it's gonna be our arc length. And so what I'll do to finish this up, well, what is a square root of dx squared? It's just dx. And so I can actually put a dx outside of this integral. And then have 1 plus dy dx squared inside. And this is equal to arc length. Now because of the dx out here, I need an infinite number of these. I'm not 100% sure where in my derivation I needed to introduce the integral symbol. This is my, like, I'm doing this from memory. I'm trying to have this develop naturally. So let me see, what did I miss? Okay. So the idea was if I wanted an infinite number of these, then I would take the integral from a to b. So arc length formula, if, like, let's say I wanted to find the length of this curve from here to here, meaning like if I took a tape measure and just traveled along and like got it perfectly, it's a really, really nice formula. It's just go from a to b, square root of 1 plus f prime of x squared dx. I'm not interested in doing these by hand. I'm sure that we could. So, and they use an L for this. Arc length is equal to that. This is one of those formulas that is it's actually gonna rear its ugly head. I said it's good looking. It's gonna rear its good looking head multiple times this year. And if you kind of have this format, then it's easy to kind of slot it into the other formats that we're gonna see. And for me, what makes this really easy to memorize and easy to remember is that it's like a squared plus b squared square root. I guess I shouldn't be using a and b because we use a and b here. Like something squared plus something squared, and it's under a square root. The other formulas that we're gonna see this year, instead of having a 1 plus f prime squared, it's gonna be like something squared plus something squared. Yeah, this is our arc length formula. And then we'll get to surface of revolution later. So, arc length. Find the exact length of the curve. F of x is equal to 4x. From x is equal to 0 to x is equal to 3. Verify geometrically. I added an extra c in there. So, literally, for number 1, go from 0 to 3, square root, 1 plus, what's f prime? If f of x is equal to 4x, f prime of x is equal to 4, okay? Wait. Maeve got a barn for Christmas. She must have pulled it off of the couch.
Was it full or anything?
It might have had a little bit left. I was gonna grab her a new one.
Okay,
yeah. So, well, 4 squared is 16 plus 1, 17. I could do this integral by hand. Darn it, okay. Because this is just a number, right? So that means that the integral of this number is just root 17x evaluated from 0 to 3. So then it's going to be 3 root 17 minus 0 root 17. So I got 3 root 17 as my answer, as my exact answer. Here's the thing though. Y equals 4x is like, it's like straight line, right? So if I'm going from 0 to 3, I'm trying to find this distance here. Shoot, that's just a triangle, right? Where its base is 3 and its height is 12. Is that right? Right, because it's 4x, so then 3 times 4 is 12, yeah. So 3 squared plus 12 squared is equal to c squared, and so that's 9 plus 144 is equal to c squared. It's 153. I'm going to guess 153 is divisible by 17.
Oh, yeah. That really hurt.
I'm also going to guess that it's divisible by 9. So I'm going to use 9 here. 9 times 1 is 9. 15 minus 9 is 6. Wow, who knew? 9 times 17 is 153. So this is 9 times 153, right? So, I mean 9 times 17, sorry. So I take the square root. The 9 can pop out as a 3, and the 17 stays 3 root 17. So we can verify that just using basic algebra. And so if you want to find the exact length of a curve and it's a straight line, I would just use the Pythagorean theorem. But you can absolutely use... Is it behind you?
Yeah, sorry.
Here.
Can you get that set?
So like for this one, y equals 5x minus 2, from x equals -1 to x equals 2, you could totally draw the picture. It's a line. Do the hypotenuse. You just do the geometry. Honestly, though, I don't really feel like it right now. I'm just like, why don't I just go from -1 to 2, square root of 1 plus f prime is 5. Why don't I just do that? And this is where, like, if you want, you could use your calculator to get the integral, or you could, you know, whatever you want to do, but it's what, 26? So it's going to be 2 root 26 plus 1 root 26, so 3 root 26. So I'm getting, kind of skipping some steps and doing it in my head. Because I'm so smart. No, 25 plus 1. And then it's going to be root 26 times x, evaluated from -1 to 2. So when we plug it in, it's going to be minus -1 root 26. That's why it turns to positive. So, all right, find the exact line. Okay, so in general, if we have y equals mx plus b, what's y prime equal to? Right? And so if we kind of look at what happened here, in general, it's going to be go from a to b, square root of 1 plus m squared dx. And so if we, well, this is going to be some number, right? 1 plus m squared is a number. So it's going to be 1 plus m squared times x, evaluated from a to b, which is going to be b times our square root minus a times our square root. Also put factor of b minus a out, or factor the square root out, and you're left with b minus a. Yeah. So if you ever wanted to know the length of any line, that's the length of any line from, okay, I'm kind of downplaying this just a little bit, but so far today, we've used the basic tools of calculus, because let's face it, the integral is a basic tool, and the derivative is a basic tool. I'm not saying that they're always easy to use, but we've used those foundational ideas to develop a new formula that will find the length of any curve ever. If that's not just a little bit amazing, think about it some more. We started from scratch and developed something that works universally. And then using that, starting from scratch, with that, we developed this length of any line, no matter how steep or shallow the line is. Now we know how long the line is from a starting point to an ending point. That's pretty cool that we were able to use calculus and get these ideas. Did you hear that car that was accelerating very quickly? I did. That guy is cool. Sorry, shouldn't assume it's a guy. That person is cool. Sorry, shouldn't assume it's a person. Just kidding. All right. But it definitely could be a girl doing it. Girls like to drive fast too. Let's see. There are very few functions other than linear ones for which the arc length integral can be taken. One of them is this. Stu's like, okay, usually we have to use our calculator, but let's do one more that's nice. So he says x to the 3/2. Let's talk about what x to the 3/2 becomes when we take its derivative. Let's see. Right? Subtract 1 from our exponent. So when we square this, this literally means therefore, each of these pieces kind of get squared individually. 3/2 times 3/2 gets us 9/4. And then x squared times x squared gives us x. So if I want to find the area under this, or not the area under this curve, if I want to find the exact length of this curve from 0 to 4, I should just be able to go from 0 to 4, that, and find it. Okay, this is a simple U substitution problem that I'm not going to do. The lazy response here is like, I've already passed integrals. I don't need to do more integrals. And let's talk computer science for a second. Why is this okay? Why isn't this not writing 9 over 4x? The way that the calculator reads what I wrote here, the calculator literally reads plus 9 divided by 4 times x. That's the way that it's reading it. And so it performs PEMDAS like a champ. So it does plus, oh, it does that at the end, right? It does multiplication and division from left to right. So it does 9 divided by 4. It gets that 2.25 and then multiplies it by x, which is why I'm not required to put this in parentheses here. When in doubt, throw it in parentheses, no big deal. So here's another little trick that I like to do. Since our answer likely has square roots in it, I like to square my answer that I get here and convert it to a fraction. Dang. Dang. All right. So sometimes squaring what you get will show you what it's the square root of. Or you can just go ask Braden because his calculator will do it for you. But, you know, future years, this won't make any sense. I'm going to have to refilm this video. Braden, who's that? But anyway, I got 82.327. All right, now we get this kind of stuff. At time t equals 0, a bug crawls along a path this. T is measured in seconds. F of t is measured in feet. What is the average speed of the bug over the first 6 seconds? Average speed. All right. So let's see, we have f of t. So this function here is position, right? So average speed means average f prime. Well, the way that we do average f prime is by using f, right? F of b minus f of a over b minus a. So I did some thinking before I started talking about this. Speed is always a positive number or 0, like a speedometer on a car. If we're going backwards, we don't say that we're going negative. We just say the absolute value of the speed of the velocity. So, but looking at this, because it's a t squared plus 2 in here, that's never going to be negative. So I don't have to think too hard about this. I can just use the average f prime formula, which says f of b minus f of a over b minus a. And if you think for 1 second, or for 6 seconds, because I'm going from 0 to 6, that I'm doing this by hand, I don't know what you're thinking. I'm going in here, and I'm going to write this function in here. Let's see, 1/3 parentheses x squared plus 2 parentheses to the 3/2. Okay, so I have f of x in here now, and I can go to my table, and I can calculate this out, no problem. So f of 6 on my calculator screen I see is 78.083, and then f of 0 I see is 0.943. b minus a, 6 minus 0. So let's see, 78.083 minus 0.943. Silly me. Divided by 6. Oh. All right, so don't use that fraction because this is using an approximation to begin with, so we want to keep using the approximation. Do they give me units? Oh, feet, okay, and they give me seconds. So feet per second, because it's a velocity. It's the absolute value of our velocity. So that's our average velocity. Also happens to be our average speed. Oh, then it says, at what time k is the speed of the bug equal to the average speed of the bug? Well, so speed, like we said, is the absolute value of velocity. Well, let's find the velocity here. That's just f prime, right? So I'll bring the 3/2 out front. Leave the 1/3 there. Leave the inside alone, right? And then multiply by the derivative of the inside, which is 2t. Just doing chain rule. So we can do a little bit of cleaning up. I can cancel the 3's. So I can look at this as 1/2. This is to the 1/2, so it's square root. Right? So now we say, when does this equal what we just got? And again, if you think I'm doing this by hand, what I'm going to do, I should show you, like, I'm going to do super fancy. So I got that, right? I'm going to click store. Nope. Let's try again. Now that you can actually see the buttons I'm pressing. So I got this, right? I'm going to click store, and I'm going to pick a letter for it. I'm going to pick O, because I can. Because that's my wife's name. So here's our function, but I don't want to know what my function, when f of x is equal to, or f of t is equal to that 12.857. I want to know when the derivative is equal to 12.857. So I'm going to show you like the super lazy way to do this. Since I just deleted it, I'm going to do like a more normal way, but oops. What I meant to do was push alpha O, right? So we just got O. I don't have to retype anything. And then I can go to my graph. Oh wait, I should zoom fit. So where they intersect, that's our answer, right? So I do second calc, intersect, first curve, second curve, guess. I got 3.449 seconds. That's what I got for part B. But let me show you, there's a trick we could do here. So instead of actually calculating the derivative by hand, I had the original written in here, right? What I can do is I can actually go math and derive. I can use the derivative, and then I have to put y1 in here. So I go alpha f4, y1, and I say x is equal to x. And so what I'm going to do now is I'm actually going to find the derivative of the first function, and that's going to be what I graph here. And so I don't know if you know this as well. Here's another little calculator trick. If you click enter on these equals, it won't graph it if the equal sign is not highlighted. So like if I hit graph right now, nothing shows up. But now if I go in, by default it's highlighted, because by default they assume you want to graph. So we can go in and we can actually have what the calculator is doing is it is brute forcing this derivative. It's going point by point and it's calculating it numerically using Euler's method, which we are going to learn in a little bit. So now I can say, well, I knew I wanted O, right? That 12-point stuff. And now I can do intersect. Let's see how close we get. 3.449, the exact same number. So, little cool trick. Really, 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 really useful, especially when finding derivatives is not something we feel like doing. I'm a little confused why that question is in there. That's not anything about arc length. Cool. What? Anyway, find the length of the given curves between the indicated values. Set up and evaluate using a calculator. You don't even need to, like, honestly, you don't need to evaluate this. As long as you get the ideas. If you want to evaluate it, Stu's probably got it in his book. So y is equal to e to the x. So what's y prime? E to the x, right? So y prime squared is going to be e to the x squared, which is going to be e to the 2x. And if you don't know how that works, well, it's e to the x, right? And we add those exponents. Another way we do it is we distribute that too. Works the same way. So a is going to be the square root 1 plus e to the 2x dx from 0 to 2. If you need the practice, I do recommend going in, typing at see if you match with Stu. Remember, his stuff is in our Schoology page. So b, y equals tangent x. Well, that means y prime is equal to secant squared x. So y prime squared is going to be secant squared squared, or secant to the 4th. So this is going to go from 0 to pi over 4, square root of 1 plus secant to the 4th x dx, right? And part C. We got y is equal to 4x minus x squared. So then y prime is going to be off screen. Y prime is going to be 4 minus 2x. So then we can just throw squareds on it like that. You don't need to FOIL all that out. And then it goes from whatever the heck a and b it wants, 1 to 4. So you could just say 1 plus that. You know, if you really want, you could say 1 plus 16 minus 16x plus 4x squared. I wouldn't. This, like, we're making more work for ourselves at this point, and why would we bother doing that? D. All right, part D is x sine x. So this one, our y prime, is going to be, I'm going to do product rule, and when I do product rule, I take the first derivative first and the second derivative second. I know a lot of people do it the other way around. Totally fine. So 1 sine x plus x cosine x, and then I have to square this. No, I'm not going to do that. So here's, if I was trying to calculate this in my calculator, this is worth doing. So let me make sure I'm in radian mode. Remember, in physics class, a lot of times you're going to be in degrees, and in our class, you're going to be in radians. It's going from 0 to 2 pi. Here's the cool thing. I'm going to call this a of x. So I would only have to write that instead of having to write a big mess. But in my calculator, what I can do is x sine x is our original function, right? Well, then I can make y2 its derivative. So d dx of our original function here's where this is awesome though. Now that I have that defined as y2, what I can do is I can say, all right, now we're going to take the integral from 0 to 2 pi of the square root of 1 plus my second function that I have in there squared dx. And if you remember, the second function that I have in there was my derivative. So it takes a lot longer because it's numerically getting the derivative and then square. Like it's taking a lot longer, but that should work. That should work instead of having to do go from 0 to 2 pi of the square root of 1 plus parentheses sine x, close the parentheses, plus x cosine x, close parentheses, square dx. It's like, which one of these was less work for me in my calculator, and which one am I more prone to make errors in? Like, this one was less work. I'm more prone to make errors in this one. So, highly recommend learning those methods. Cool. So that covers arc length. Next time we'll cover surface of revolution. It's just another formula. We're going to speed through it, and then you'll have time to. It's a video, so you're watching this whenever you want. But my idea is we'll learn a little bit extra, and then you'll have the rest of the time to work on homework. So, hope this was helpful. Bye.